Okay, so bottom of page 17, we've got a couple questions here. Number 6, a skier descends a slope, and FYI, it should be 30 degrees. We forgot to superscript that last 0. So the slope, the ramp is 30-degree angle. We'll assume it's with the horizontal axis, as is the norm. And we're going to have a coefficient of kinetic friction. Kinetic, right off the bat, it tells us what's going on with our object. It's moving. Okay, so we know that. And they tell us 0.1. So remember, your coefficients are from 0 to 1.0 typically. And so this is a really low friction, which it should be. I mean, in my head, I see a snow skier, right? Calculate her acceleration and then the speed she will be going at 4 seconds. And so hopefully you know B is going to have us do what topic? Kinematics. But you can't do kinematics without the acceleration. And without the kinematics, you can't solve for acceleration. In other words, what's going to be our topic for part A? We got to solve for acceleration with forces. And so it all starts, step 1, don't forget, is what? Diagram. And so there's not any kind of picture going on here. So maybe we draw a picture. And it doesn't matter if it slopes to the left or slopes to the right, just draw an incline. And we'll assume this snow skier is not doing moguls. Do y'all know moguls? Olympics are coming up in February, right? So moguls are those little bitty hills that it's just little hill. Their knees bob up and down whenever you watch a straight ahead video. So we'll assume it's not a mogul. We'll assume it's not slalom, which is your back and forth, left, right. We'll assume it's just straight down, right? And so we know this angle is 30 degrees. So snow skier right there. And that's just a picture. We need a force diagram. Now I'm going to draw it separate. What forces are acting on our object? Oh, did they give me the mass of the skier? No. So what's going to probably happen to that mass in the future? It's going to cancel. Okay, so hold on to it. No, you don't need mass for kinematics. Remember the first month and a half, we never talked about mass, right? It's independent. All right, what forces are acting on our skier as they go down the ramp? Descends. Descends lets us know they're going down the ramp. What do we got? Gravity. Does gravity care that we're on a ramp? No, it goes straight down. What else? Normal force is drawn perpendicular to the surface. So based on how I have this ramp drawn, it would be up, tilt your head to the right. And it should be smaller than FG. What else? Friction. So once you recognize descends is down the ramp, friction's going to act up the ramp, smaller. And it's kinetic friction, which FYI, kinetic friction is less than your static, which they didn't give us static, but just FYI. Oh, okay. Any other forces acting on the person, the object? No, and just a reminder, don't draw a downward force and call it F net. If you notice, I've never written F net on a diagram, right? The only forces you draw on a diagram are gravity, which comes from the gravitational field, and then contact forces. F net is neither. And don't draw down the ramp force and say F motion or FA. No one's pushing them down, right? We're just letting gravity bring it down the ramp. Well, I've already got gravity. But one thing you can do with gravity is draw in the components. So remember with ramps, the axis tilts. And so friction is on your new parallel axis. Normal is on your perpendicular axis, but gravity does not tilt. And so gravity is going to be the one to have components. And so here's your last viewing of me drawing my gravitation triangle. I always start going opposite FN because 99% of the time, FG perpendicular is equal and opposite to your FN. And then that's on the new y-axis. FG is on the old y-axis. So if the x-axis tilts 30 degrees, so does my y. And so between FG perpendicular and FG, I find that 30-degree angle. And then to finish the triangle, I like to make FG a right triangle. Make sure FG parallel is actually parallel to the parallel axis. And your final check is what? FG should be what part of the right triangle? The hypotenuse. And so if you draw it in and you're like, oh, that doesn't look like the hypotenuse, make some adjustments, okay? On test day, use pencil so you can erase, yes? But it should be that your components are separated by 90 degrees. Good on the diagram? Now to solve for acceleration, ask yourself, which dimension is this skier accelerating? The parallel. So we want to write an FNet parallel, or you can call it FNet X. It's the new X direction. And so they're going downward. So maybe I need to define my positive direction. I like to go forward as positive. And with that designation, what force is pulling the person down the ramp? Gravity parallel. So I'm going to say FG parallel minus, who's resisting that forward direction? Friction. And that's it in the parallel direction. So let's solve for the acceleration. I don't see it, but say it with me. FNet equals MA. That was a good amount for the Monday morning. And there's that mass we don't know. Don't cancel it yet. Equals, and we have a special equation for FG parallel. You may have memorized it. You may want to memorize it. And if you don't, if you're like, oh, I'm not good at memorizing, look at your triangle. Find your FG parallel. Remember, gravity, FG, mg is your hypotenuse. What trig function will we use for FG parallel? Sine. I don't know what just happened with my projector. Okay, so we'll use the sine function for the parallel component. And so remember, hypotenuse times your sine function. I'm going to go straight for mg, right? Isn't it true that our gravitational force, AKA the weight, is mass times gravity? Okay. Minus, what's our newish equation for force of friction? Mu k times Fn, normal force, right? And so what did we say was true about normal forces on a ramp? Right, it's FG perpendicular. So now look at FG perpendicular. So to solve for FG perpendicular, cosine. So I am doing two steps in one. So listen to my words. Force of friction is mu Fn. But to save a little bit of writing, Fn on a ramp is mg cosine theta. So I'm gonna go straight for that. Now, notice all three force terms are broken down into mass. Now we can divide the whole thing by mass, and what's gonna happen? It's gonna cancel. And now we can solve. It's already isolated for acceleration. And so acceleration parallel to the plane to the ramp. G, I'm going to use 10, sine 30, minus mu k, which they said is 0.1, times gravity again, but now cosine 30. And it's our first time, so make sure your calculator's in degree mode. So sine 30 is the 1/2 of 10. So I know that the first part is 5. Let me know what you get for the friction term. Say louder. 0.87? Okay. And so your acceleration down the ramp would be what? 4.13 meters per second squared. Everybody good with that? Now, does mass cancel out in every single problem? Should we start getting cancel happy? No, okay? Only if it's every single force term is broken down into every single mass term, okay? When is it not? For example, we've seen applied force, we've seen a tension force maybe. Now maybe tension cancels, but mass didn't in that situation. But just be careful, make sure you're justified before canceling out the mass. And y'all, good test taking strategy, it's pretty much true if they don't give you mass in the first place, it's gonna cancel, okay? Or you would just keep it in terms of mass. I think we did one prior where we had our answers something m, right? All right, I'm gonna go and skip over the kinematics. Hopefully y'all can do that part by now. Let's take a look at number 7 and then we'll move on to lab. Number 7, not a ramp. So we're going back to just typical angles, okay? We did that with, I guess, the first half of forces. You're driving 25 meters per second when you see Bambi in the road. Oh no. We don't want to hurt Bambi. No one gets hurt in physics land, right? The coefficient between your tires and the ground is 0.8, which should make sense. Rubber in the road, you want a good amount of friction. You slam on your brakes, praying that friction is great enough for Bambi to survive. In other words, you don't hit Bambi. Draw a free body diagram. We already knew we had to do that, right? You didn't need to be told. Write your if-net statements. We know to do that, right? And then D, what we're really solving for here, what angle, oh, by the way, our car, apparently we have a fuzzy dice hanging from the rear view mirror. Maybe some of you have something hanging, right? What angle will the fuzzy dice make with the vertical? Make sure you catch that piece. While you are desperately trying to brake the car in order to stop. So we did this back in, a couple weeks ago now with the lady hanging from the helicopter, right? I demoed with my microphone. When you're braking, the objects that we're talking about, they want to be moving. So if I try this again, watch the braking time, watch the braking portion. So I got to speed up, but then watch the braking. So I speed up. Microphone goes forward, right? Objects in motion want to stay in motion until the tension pulls them back and says, no, we're stopping now, right? And so if you look at the little cartoon, the car is moving forward, but during the braking period, the fuzzy dice wants to keep going forward. And so what forces would be acting on our fuzzy dice? We got gravity. Gravity always down. Hopefully you know that by now. And tension would be going up and parallel to the string. During the braking period, it would be up and left. And draw it bigger. Okay, if you don't remember why it's bigger, just hold tight. And that's it on the dice. Now notice the prompt was all about Bambi in the car, and now our question's about this fuzzy dice that's in the car. What's going to be the same for the dice and the car? What connects them? Acceleration. So the acceleration of the car is going to equal the acceleration of the dice. Now, before I write my FNet statements, I'm going to do what I'm not going to do on the May exam, right? College Board says do not draw components. But most people need to see the components in order for them to appear in your FNet statement. And so who's got components? It's the tension. Oop. There's a horizontal component to the left and a vertical component up. And the angle we're looking for, read carefully, they want the angle with the vertical. Okay. And so our FNet statements are going to be what? FNet X, there's only one. Now I haven't determined the forward direction. I'm going to go with forward for everybody. The car and the dice, based on the little picture given, would be to the right. Well, there's no rightward force on the die. There's only a leftward tension pulling it back, right? And so it would be a negative FTX. What about FNet Y? And I'm going to leave a little space. We've got two vertical forces acting on our object. And I haven't really defined the positive direction. We'll go with standard. There's not any movement at all vertically. Okay, and so it's not going to matter. But FTY can be positive, then minus FG. Well, in both cases, FNet equals MA. So MAX, MAY. Which one zeroes out? Which one? Mass. Well, not mass. Which acceleration zeroes out? The vertical. We're not moving at all vertically. The car and the dice is moving in the horizontal. So this acceleration zeroes out, telling us what's true about FTY and FG. They're equal. So remember earlier I said draw the tension bigger, which I'm looking at mine now, and I wish I'd done a little bit bigger. But it's the vertical component of tension that balances FG. Equal and opposite, Newton's first law. It balances on one object. What about the horizontal? And so they didn't give me this acceleration, right? But we know it's equal to the acceleration of the car. So let's do a little bit more with our FNet statement. And then we'll transition to the car to figure it out, okay? Hopefully you know by now, if you have more than one thing unknown, you got to do more than one step, right? FTX. Actually, we can plug in functions for FTX and FTY. Notice your X component is opposite theta, because they said theta is with your vertical. So what could we plug in for FTX? I could use the sine function. So it's FT times sine theta. Oh, wait a second. They didn't give me the mass of the dice. They didn't give me the mass of anything. Mass should cancel. But the way I have the X statement, it doesn't cancel, right? Keep watching. This is so fun, isn't it? FT. Hold tight to FT. Go to your vertical component. FTY, what could we plug in? Which function? FG, yes, it'll equal FG, but just for FTY, the one here in the vertical, cosine. It's adjacent, right? So we can say it equals FT cosine theta. Both equations have FT in them, right? I can do a substitution. That equals FG. What is equal to FG as well? MG. And so notice, look at all these unknowns. I don't know the mass. I don't know the acceleration. I don't know the tension. I don't know the angle. Oh my gosh, how in the world are we supposed to solve for this, right? Well, look at your other statement. We don't know mass, we don't know tension, we don't know theta. Well, let's try to eliminate some of those, right? They both have tension, and for sure we don't know the tension force. What if we solve the y equation for tension and then substitute it up above? Substitute it out, right? And so Ft would be mg over cosine theta. Plug that in right there. Is everybody with me on the why we're doing this? So then we have max equals, now the negative is there because we're slowing down, pushing on the brakes, right? Negative acceleration, negative net force. And then I have mg over cosine theta plugged in for the tension times sine theta. So at this point, what do you notice? They don't cancel, right? So if you think about sine theta over cosine theta, I don't remember the laws of trig, but that reduces or simplifies to tan theta, right? And you can kind of show that sine theta is opposite over hypotenuse divided by adjacent over hypotenuse. And if you multiply by the reciprocal, what happens to hypotenuse? It goes away, and we're left with opposite over adjacent, which is defining what function? Tan theta. And so we get mg tan theta, bring everything else down. Now what happens? Oh, I got masses on both sides. And remember, that was one of our unknowns. They didn't give it to us. We're not solving for it. And so we can actually divide the whole thing by mass. And look at that. Our 4 unknowns just went down to 2. So what do we still not know? We're looking for theta. That's our final answer. But we need this acceleration. Hopefully somebody's been wondering, they gave us that car information and we haven't used it yet, right? Here's where we're going to switch over and use it. Remember that this is the acceleration. This is a FNet statement for the dice, okay? But the acceleration of the dice, we said, is dependent on the car. So now let's take a look at the car's force diagram. So pause on the dice. What about the car? It's got its own gravity. Oh, we don't know that, do we? Did they give us the mass of the car? No, all they gave us was the initial velocity, coefficient, and then they said we're going to stop, or that's the goal. So just hold on to it. What else do we know about the car? Forces. Normal force, balancing the vertical, and friction is going to act what direction? To the left. And they gave us the kinetic coefficient. So I think they only gave us one. We're moving. They gave us an initial speed. It's moving. Now Fn and Fg are going to balance out, right? And so the net acceleration is in the horizontal. This is of the car. And it's going to feel similar, but now the only horizontal force on the car is that frictional force. It's going to bring it to a stop. Fnet equals ma. So this is the mass of the car. And there's that horizontal acceleration that we're trying to get back to. Equals a negative, what's our newish equation for friction? Mu k Fn. And what's going to be true about the normal force of the car? 100% equal to the gravitational force. So mg, hey, do I need the mass of the car? No, divide both sides by mass of car. It cancels out. And so the acceleration of the car is equal to negative mu kg. Now, whether we take that and plug numbers in, or maybe we go ahead and plug it in up here. So now I'm going to go back to blue. If the accelerations of the dice and the car are equal, then I can say a negative mu kg, that's the acceleration, equals a negative g tan theta. Oh my goodness gracious. Now I've told you don't get cancel happy, because most problems you don't cancel so much, but this one we are. What cancels at this point? Gravity and the negative, right? And so notice all that mess simplified to tan theta equals mu k. They gave us mu k, they said it was 0.8. Now how do I solve for theta? Inverse tan. Which is what? 38.7 or 39 degrees. And again, since in my picture, I started it with the vertical, just a reminder, they said find the angle with the vertical. We did that from the start. I'm just reminding everybody, it's 39 degrees from the vertical. Because normally, if this car was at rest or moving at a constant velocity, right, equilibrium, it would just hang straight up and down. It's in the vertical normally. Good deal? And you're like, gosh, isn't there an easier way to do that? Right? And so if we had recognized in the diagram earlier that the acceleration of the dice was equivalent to the acceleration of the car, when we did our force diagram right here, we were looking for that angle. So just kind of not necessarily shortcut, but a simplification. If you recognize, oh, the vertical is equal to mg, and the horizontal tension is dependent on the horizontal friction of the car, right? No, actually, we couldn't have done that because this was the mass of the dice. Those are two different masses. Never mind. Guess we would have had to go through. Okay. Okay. Questions before we move on to lab? All right.